Hello, everybody, and welcome back to our first technical lecture with this energy harvesting system course to be delivered for senior students as an optional module. Let's now go to our first chapter, which is, as mentioned earlier, this is a refreshing chapter with some semiconductor and optoelectronic principles that most likely you have already studied before, but we are just flashback on this general principle that we are going to use mainly with studying light harvestors and also somehow with thermoelectrical and piezoelectrical material as well. So let's start with sharing the PowerPoint slides and with this chapter with optoelectronic principle under the 22 ECE 32H. Okay, so let me first mention that you can find a detailed content of all these material in this reference, which is Principle of Electronic and Electronic Materials Devices by CASAP. I think those students who have attended the solid state module with me already know this reference, and we already used it before. Okay, so let's start together as usual. First of all, the basic element of any electronic device, including energy harvesters, is the material. So in order to fabricate an appropriate, or between quotation, an optimum harvester, you should select an appropriate material for this harvester. So in the first of all, we have to know deeply what are the different classifications of material. And herein, we have to highlight this different classification with respect of the electrical perspective or the electronic perspective of a material. For example, if we have any rod of a material, and I told you, please, I need to investigate the electrical conductivity of this material. Most likely, what you are going to do is as following. What you are going to do is you will going to connect this material with a potential source, an emitter, and in parallel a voltmeter. And you will use a variable DC supply. You are going to vary the volt and measure or observe the variation in the current so that you will have voltage versus current. Then, using this relation, if you go to plot this relation for using Excel, for example, the slope of this relation will give you 1 over the resistance. Knowing this resistance and knowing that R equal rho times L over A, well, rho is resistivity, L is the length of the material as indicated, and A is the cross-sectional area, as you can find it here. So long L and A, because you have the physical dimension of the material, you can easily calculate rho, which is the resistivity. Now, sigma, which is the conductivity, equals to the reciprocal over 1 over rho. Then, by doing this simple experiment, you can investigate the conductivity of different materials across different conditions. Perfectly. Then, if you did this experiment for different material, for each material, you're going to calculate the sigma using the equation here. Then you will find something like that. Some materials will be or will result in conductivity, which is extremely high, in the orders of 10 power 6, power 7, and so on. Other materials will be with a very, very low conductivity, like 10 power negative 5, negative 4, negative 10, negative 17, and so on. And a third group of material will be in an intermediate conductivity, not as high as the first group and not as low as the second group. Accordingly, people start to classify the materials here as conductive, semiconducting material, and insulators of the electrical materials. But what is the reason beyond this conductivity? So why copper is a conductive? And why glass is an insulator? And why silicon is a semiconductor? If we consider that a conductivity is a proportionality of the availability of a free carriers. So materials with higher free carriers will result of a material with higher conductivity. You know, of course, the word carrier, including both electrons or holes. So, for example, if we have a material like copper with one valency electron in the outermost energy level, accordingly, the material or electrically, this electron is weakly bound to the nucleus because it's only a one electron in the energy level, and it's in the most far filled or partially filled energy level. So it is very easy to kick this electron out to a higher energy level, and then this electron become a free electron. Accordingly, each atom of the copper material can donate with an electron. Knowing that in 1 mole of a material, you can have something like a 10 to the power 22 or 23 atoms. That means that for each atom, for each mole, you will have 10 power 22 or 23 electrons, free electrons. Alternatively, for this example, where we have 7 electrons in the outermost energy level, obviously these 7 electrons are highly bounded to the nucleus. Accordingly, you are not capable of being, or you are not capable of making any of them free. That's why it's an insulator. Thirdly, you can find a case where you have 4 electrons in the outermost energy level. Herein, it is equally fair between making this electron free or making this electron strongly bounded to the nucleus with another 4 electron in a covalent bond, for example, and then this is a semiconductor material. So, by definition, a semiconductor material is a material which has 4 electrons in the outermost energy level. And it can show this tetrahedral structure either in this direction or what we can call a zinc blende structure whenever it's a compound semiconductor, like, for example, when we consider silicon. So, sorry, gallium arsenide. So this is a silicon diamond structure, and this is a tetrahedral structure with gallium arsenide. As you can see, from an atomistic perspective, both are most likely the same. However, in a diamond structure, all atoms belongs to the same material, while in a tetrahedral structure, it's a mixture of 2 different materials, as you can see. Okay, so this what we can call an atomistic level of a material. We consider each atom individually, like we did here in this example. We consider each atom individually of a material. So I pick up a single atom of a silicon and I start to study this single atom. However, realistically, it's hundreds and millions and billions of atoms combined together. That's why we have to scale up to what's called the band theory. I think this will help you to understand the band theory. Let's start with it. So let me just make it clear. Okay, that's great. So when we start here, this is a silicon atom. The example here will be considered for a silicon atom. So for a silicon atom, as we just see, we have 14 electrons. These 14 electrons are collected as 2 electrons in the outermost, in the most inner energy level, then 8 electrons, and then there are 4 valency electrons, as you can see here. Now, what happens if, or in the reality, this silicon atom is not alone? There is a lot of silicon atom, neighbor silicon atom around it. So once we go here, we will have another atom. This another atom already have its own energy levels. What will happen is each energy level of the second atom will overlap with the corresponding energy level of the first. So instead of having one energy level here with 2 electrons, you will have 2 energy level with two electrons. And same here and same here and so on. Then you will have a third energy level, as you can see. This third energy level, this third atom with this third energy level overlap with the old 2 energy levels till we reach this shape. In this case, my dear students, the energy level concept is transferred to what's called an energy band. As you can see here, energy bands is the accumulation of energy levels having the same energy. So instead of having a single energy level, it becomes a band of levels. That's why we call this an energy band. So here we have an energy band, here we have energy band, here we have an energy band, here we have an energy band, and so on. But are all these energy bands are the same? Let's see. I will scale it up a bit. Okay, let's do it here. Okay, so this first energy band is completely full. Why it's completely full? Because each level can be occupied by 2 electrons. Please remember your high school chemistry classes. And it already exists. Per each energy level, as you can see, there is 2 electrons. So this is a completely filled. It's completely occupied. On the other hand, we call this band as a core band. Why we call it a core band? Because in this is the most near band to the nucleus, which means the attraction force is maximum. So it's very difficult, let me say it's impossible to break the bond between the electron and the nucleus in this band. So the first energy level here is a completely filled energy level and very close to the nucleus, which means that this energy level is of an unused effect for electronics, because usually, as we just mentioned, we are targeting electrons which capable of being free electrons. Same apply here. Each energy level can be occupied by 8 electrons, and we already have these 8 electrons. So it's a completely filled energy level. However, here there is something to say, because this energy level is partially filled. Each energy level can occupy with 8 electrons, but we only have 4, which means that this is a partially filled energy level. Alternatively, this is a completely empty energy level. So our area of interest as an electronic engineers is this portion. In this portion, we have a partially filled band, which is a valency band, and we have a completely empty band, which is a conduction band. The target is for semiconductors is to give energy to the electrons in the valency band to be capable to jump to the conduction band. Once the electron jumps to the conduction band, that means that it loses its bond here and it's become a partially free electron. And as I just mentioned earlier, the higher the number of free electrons, the higher the conductivity. So this is basically what we already know under the name of an energy band diagram.
So in semiconductors, we have a valency band, a conduction band, and between these bands, there is what's called the forbidden gap or energy band gap. Under certain intrinsic or extrinsic condition, you can give some energy to this material, so some electrons can jump from the valency band to the conduction band, generating what's called hole in the valency band and a free electron in the conduction band. Alternatively, in metals or in conductors, we don't need to do these efforts. Electrons can move freely from the valency band to the conduction band. That's why conductors are conductors by default. You don't need to seek for intrinsic or extrinsic condition to be a conductor. It's a conductor by default. It has a free electrons by default. On the other extreme, as you can see here, for insulators, the energy band gap is very large. So whatever the energy you give to the material, no electron will be able to jump to the material, and there is no possibility for free electrons. This is how we can distinguish between conductors, insulators, and semiconductors. But going more and more into a physical model about the physical nature of this energy band diagram, because what you are seeing here now is just a demonstrative chart to express or to demonstrate the energy band diagram. But from a quantum mathematical perspective, these energy band gaps are given in terms of what's called the EK diagrams. The parabola in the upper side represents the conduction band. The parabola in the downside represents the valency band. Herein, we have two possibilities. So the top of the valency band can be aligned with the bottom of the conduction band, as you can see in this graph. And this is what we call a direct band gap semiconductor material. Or the bottom of the valency band may be shifted to the top of the conduction band. For example, if it looks like that. So as you can see here, the top of the valency band is not aligned vertically with the bottom of the conduction band. So in this case, we call this material as an indirect band gap semiconductor, like the case of silicon. Silicon is an indirect band gap semiconductor material, while, for example, gallium arsenide is one of the most famous direct band gap semiconductor material. Maybe if you remember our laser lecture 1 year ago in our optical course, you remember that in order to make an stimulated emission of radiation, you need to have a direct band gap material. But here we only consider the y-axis. What about the x-axis? What about this K? Actually, K is what's called the weight number, and its physical meaning is related to the P or the momentum. So as you can see here, the variation in the x-axis indicates a variation in the momentum. So for a direct band gap material like this case, what you are going to do by moving from the valency band to the conduction band or vice versa, you are going to make a change in energy without any change in momentum. However, in case of an indirect material, in the case of silicon, as I just demonstrated, you need to make a change in both energy and momentum in order to move from one state to another state, or from one band to another band. Here comes with a very important demonstration or very important concept, which is the effective mass. And this effective mass is associated with another important concept, which called heavy carriers and light carriers. So let's go into this concept. Quantumly, effective mass is demonstrated as the reciprocal of the second derivative for this EK diagram. So, for example, by considering these two graphs, here, if we assume a parabola curve, either in given curve number 2 or number 1, so the first derivative of this parabola will result with a straight line. So we can plot it here, for example.
something like that. And let's use another color here, something like that. So these are the first derivative for graph number one and graph number two. And then with this graph number one, with this graph number two, the slope of this line will represent the second derivative of the of the EK diagram. So 1 over the slope results with the effective mass. For this example, for this case, for example, here we have that the purple line has a higher slope with respect to the red line. Then that means that the effective mass for the red particle in graph number one is higher. So we call this a heavy carrier, and the one on the purple is a light carrier. Later on, we will focus or we will describe more about what is the effect of having a light carrier and a heavy carrier. Another important aspect here, which I think that you already know it as well, which is the Hall concept. The Hall is the broken bond in the valency band. So whenever you have this intrinsic source of energy represented in temperature, at room temperature, so this energy will capable to motivate intrinsic carriers to go from the conduction band to the valency band, the valency band to the conduction band. Then a bond is broken here, creating a hole. So a hole exists whenever there is a broken bond. So let's do it in a mathematical manner. We have three types of energy. We have kinetic energy that can be represented in half the effective mass with the velocity square. We have the thermal energy, which is the intrinsic thermal energy produced or induced in order to generate electrons to the conduction band. And we have the electrical energy given as E times E. The small e represents the unit charge of a single charge of an electron, which is 1.6 times 10 power negative 19 coulomb, and the big E or this capital E is the energy. Using this equation, okay, this is kinetic energy, this is thermal energy, and this is electrical energy. This velocity, we call it the thermal velocity. This is simply because the source of this energy is the temperature. So electrons are now moving in what we can call a random walk or random motion. And this, as the energy, as the kinetic energy is an alternative to the thermal energy, we call this the thermal velocity. And on the other hand, of course, you know that K is the Boltzmann constant and T is the temperature. And as I just mentioned, that E is the electrical energy in electron volt. So now we can make a very fundamental definition here or derivation here by using the fact that the force equals to minus E times E. Here now eta appears. So here eta here is what's called the electrical field intensity. So minus E times E. E again is the electron charge. We have a negative sign here to indicate the polarity or the direction as electrons are negatively charged. And from our Newton mechanics, we know that the force equals the mass times the acceleration. Again, please remember that we are usually use the effective mass concept rather than the constant mass of an electron. And as you know that the acceleration is the second derivative of the displacement. From this equation, or from typically, let's highlight it. Yeah, typically from this portion of equation, you can calculate the velocity, but just take care between two velocities. In the previous slide, my dear student, we consider the velocity as an output of a thermal energy. So now the input is thermal energy and the output is a kinetic. So the velocity here is called a thermal velocity. However, in this case, my dear students, the input is an electrical field intensity, or in other words, the input is a battery, a source of potential. So when we're going to calculate the velocity, which is the first derivative of a displacement, by simply putting this factor in the denominator and integrate both sides with respect to time, you have that Vd equals to
E times tau, which is a time constant produced as an output of the integration, M effective times eta. Here, this is a drift velocity. Sorry, this is a drift velocity. So in the beginning, the first velocity is the thermal velocity, which is due to thermal energy, but now this is a drift velocity as a function of eta. So simply you can find that if the temperature is equal 0 absolute Kelvin, which is something hypothetical, the thermal energy will be equal to 0. So the occurrence of this thermal energy is correlated to the temperature. At room temperature, we have the 273 Kelvin, so we have the thermal velocity by default. But on the other hand, this drift velocity is a function of eta. So if eta equals 0, which is something very possible whenever you have a material under thermodynamic equilibrium without any added electrical field, so whenever eta equals to 0, this drifting velocity is equal to 0. V thermal is a random walk velocity. However, V drift is a guided velocity. And finally, this tau is called the relaxation time. Again, V drift equal E tau M effective over eta. Using this, we can call this term what we can call the mobility of a particle. So the mobility is a reciprocal function or a reverse function of the effective mass, which is again makes sense with logic that the higher the effective mass or the higher the mass, the lower the mobility, and vice versa, of course. And from here we have the concept that for silicon, for example, electron mobility is higher than hole mobility. However, this is, please remember that this is only related for silicon because this is can differ for other materials. For example, maybe one of the examples we will consider in this course, whenever we consider the polyaniline, for example, as an organic semiconductor material, and also in most of the organic semiconductor materials, the hole mobility is greater than the electron mobility. So this is mainly a function on the EK diagram. Whenever the EK diagram change, you can have a different relation between the electrons and the hole mobility. Again, this is the term Vd equals E tau over M effective going to eta, where we have J or the current density. I think you already remember this. I just need to highlight that this is a revision lecture flashing back different concepts of the different previous concepts we have already studied in different electronics or solid state courses. So J here, which is the current density, equals to number of electrons m times E, the unit charge of an electron, times the velocity Vd, which is equals to E tau over m. Herein, this is a very, of course, this is a typing mistake. This is not E, this is eta, because we have here eta. So this is eta. I will correct it just after the recording. So this is eta. And now we have J equals sigma times E, which is the very basic form of the Ohm's law, that the current density equals to sigma, which is the conductivity, times eta, the scratch version or the principal version of Ohm's law. Now, if you remember, the next step was to calculate n, which is the number of electrons. If you remember here, we first introduced this concept in this slide. This is basically a semiconductor. Whenever this T is 0, I mean at 0 absolute Kelvin, there is no electrons in the conduction band and there is no broken bond in the valency band, no holes. Once you reach a room temperature, an intrinsic temperature effect starts to appear. And whenever an intrinsic temperature effect starts to appear, some electrons, we call it the intrinsic concentration, some electrons will jump from the valency band to the conduction band, creating a hole, as you can see here. So, principally, now we are seeking for calculating this n, the number of electrons, which is typically will be equal to the number of broken bonds over the number of holes. So, to do this these calculations, we will based on the probability assumption. What is the probability assumption? It's very easy. I think we already, or you already remember somehow these basics from the foundational solid state course, that whenever you have a place and you need to know the number of people in this place, you can just do a multiplication of two functions. The first function is the number of seats in this place, which we call the energy density function. And the second is the probability to find someone in this place, which is in our case, the Fermi drag distribution. So the Fermi drag distribution simply represents the probability of finding an electron in an energy state. So at 0 degree Kelvin, as I just described, zero probability to find an electron in the conduction band, and 100% the electron exists in the valency band. Whenever you increase the temperature, well, let's go to the curve number, the green curve. So the probability to find an electron in the conduction band starts to increase, and the probability to find or not to find the electron in the valency band starts to decrease. The higher the temperature, because the temperature is the source of intrinsic concentration, the higher the temperature, the higher the probability to find an electron in the conduction band. This can be easily described by comparing the blue, the blue curve with the green and with the red curves, as you can see in this slide. And this is the function used to describe the probability of finding an electron, or the probability of finding hole, which is of course 1 minus the probability of finding electron. If f of E is the probability to find an electron, then the probability to find a hole is basically 1 minus f of E. And again, at 0 degree Kelvin, no electrons will be in the conduction band, and your semiconductor will behave like an insulator at 0 degree Kelvin. On the other hand, I just described to you that the number of electrons is a multiplication of two factors: the probability to find an electron and the possible states, or the possible seats for an electron. The possible seats of an electron is what's called the density of states. We have a density of states in the conduction band, and we have a density of states in the valency band. Logically speaking, whenever you are interested in finding electrons, you will go to this function, which is the density of states in the conduction band, because free electrons are defined in the conduction band. And whenever you have, or whenever you are searching for holes, you will go to this function, because broken bonds or holes are defined in the valency band. Now we can do the multiplication. We can multiply the density of the states in the conduction band times the probability of finding electron in the conduction band, or the density of states in the valency band times 1 minus the probability of finding electron, which is the probability of finding hole in the valency band, as you can see. And logically speaking, the total number of electrons in the conduction band will be equal to the total number of holes in the valency band. You can do this either graphically, as you can see in this slide, or you can do it mathematically here. For example, to calculate the number of electrons, again, electrons are defined in the conduction band only. So N equals AC, or integration from AC to infinity, G of E. Again, here we are, this is the density of states in the conduction band times the probability of finding electron. So this is basically the integration. Of course, this is not a very easy integration. You can go to MATLAB, for example, for a numerical solver here, where we can find a closed form here. This is a closed form for n in a function of an NC, which we call the effective density of states in the conduction band NC given in this form. Similarly, you can calculate the number of holes P by integration from EV to negative infinity. This is simply because holes or broken bonds are only defined in the valency band. G of E, again, here we are using the density of states for the valency band multiplied by 1 minus the probability to find an electron. Again, you will have this closed form for the whole with the effective density of state in the valency band. And so this is simply how we can consider the process of electrons and holes. Electrons are defined in the valency band and holes are defined in the conduction band. In the next part of this lecture, we are going to rethink or remember together the concept of Fermi level, and then we are going to move a little bit toward a new section. I believe that this section is a totally repeatable section. We already have studied this before somewhere. Now we are going to a new concept related to the optical generation and the quasi-Fermi levels after rescanning the concept of Fermi level. So in the next lecture, we are going to do this, inshallah. In the next part of this lecture, we are going to do this. See you next week. Bye.